Welcome to the deep dive. Ever wondered what really makes the motors and generators around us tick? Like, down to the basics.
Yeah, the fundamentals.
Today, we're cracking open the nuts and bolts, or maybe the mathematical foundations of electrical machines. Think of this as your shortcut to understanding the essential building blocks.
It's technology that powers, well, pretty much everything.
Exactly.
And if you've ever felt like maybe you're missing a fundamental piece of how this crucial field works, perhaps for your job or a project, or maybe you're just curious,
Then you're definitely in the right place.
we're diving into the core principles and, the different flavors of electrical machines. And our guide for this is the book, Electrical Machines, Mathematical Fundamentals of Machine Topologies, -pdf.pdf.
Right. So our mission today is pretty simple. We want to pull out the most important insights from this book. We're focusing on the core mathematical ideas and introducing you to the main topologies of electrical machines.
And the goal is really clarity. Make these concepts accessible so you can build a solid mental model without, getting bogged down in every single equation right away.
Perfect. Okay, let's dive in. Chapter 1 starts with those foundational electromagnetic principles. Where else would you start, really?
Exactly. The book starts, quite rightly, with Maxwell's equations. Now, I know these might sound a bit intimidating.
Yeah, they have that reputation.
But you can think of them as the fundamental laws governing electricity and magnetism. It's like the DNA for how electrical machines work. So we had introduced to Ampere's law.
Which is about currents making magnetic fields.
At its heart, yes, electric currents create magnetic fields. Simple as that, almost. Then there's Faraday's law of induction. This one explains how a changing magnetic field can generate, well, an electric voltage in a wire loop.
Ah, right, like waving a magnet near a coil and boom, electricity. Magic.
It's her magic, yeah. And the book immediately brings in Lenz's law here, which is kind of like the universe applying the brakes. It says the induced current always opposes the change that caused it in the first place.
So it pushes back against whatever's happening. Got it.
Precisely. And the other two Maxwell's equations, the third and fourth in their integral forms, are just as crucial. The third one tells us there are no magnetic monopoles.
Meaning no lonely north or south poles. They always come in pairs.
Exactly. Magnetic field lines always form closed loops. And the fourth equation relates electric fields back to electric charges. Charges are the source of those fields. Put those four together.
And you've got the complete rule book.
The complete rule book for all electromagnetic interactions inside these machines.
Okay, so those are the fundamental laws.
Yeah.
But how do they translate into, actual energy transfer, force, power, the things that make a motor spin?
The book seems to break down different scenarios. It does, yeah. It starts smart, looking at simpler situations first. Like, imagine a system with a moving part, an armature maybe, where you keep the electrical current constant.
Okay.
In that case, any change in the stored magnetic energy directly translates into mechanical work being done.
Right. Then what about keeping the magnetic flux constant?
Okay, different scenario. If you manage to keep the flux linkage constant, then the electrical energy you put in basically just covers any losses, like heat, and the mechanical energy you get out actually comes from that stored magnetic energy.
Interesting distinction. And then it must tackle the more complex real-world cases.
Absolutely, where everything's changing, the armature position, the current, the flux linkage all at once.
It's just probably most practical situations.
Pretty much.
Yeah.
The book walks through how energy shifts and transforms in those dynamic cases. And what's really insightful is how it links magnetic energy and mechanical force, especially for materials that respond, let's say, linearly to magnetic fields.
And that leads to the idea of magnetic pulling force, the actual tug.
Exactly. The literal, invisible force that makes things move in a motor or generator, it's converting that magnetic potential into kinetic energy.
Okay, so force comes from that interaction. And the book connects this to the power balance in an inductive circuit.
Yes, definitely. It shows how the electrical power you feed into a circuit, say a coil, gets split. Some is lost as heat, I squared R losses from resistance.
The unavoidable losses.
Right. And the rest goes into changing the amount of magnetic energy stored in the circuit's magnetic field. And crucially, it lays out the math for how the force produced relates to how the inductance changes as parts move.
Inductance, that's like how easily the circuit accepts a magnetic field, right?
Yeah, essentially. How much magnetic flux you get for a given current. If that property changes as something moves, say an air gap closes, then a force is generated.
That's a really key idea. Force from a changing inductance with position. Okay, switching gears a bit. The book brings in some essential math tools like complex phasors for AC systems. Why are those so important?
Oh, they're incredibly useful. Imagine trying to track, three different sine waves oscillating constantly, 120 degrees apart. It gets complicated fast.
Right.
Complex phasors are like a shorthand. They let us represent those sinusoidal AC voltages and currents using complex numbers. Instead of time-varying equations, you get a single complex number that captures the key info: the effective size, the RMS value, and the timing, the phase angle.
So it freezes the wave at a point in time,
Yeah.
kind of showing its magnitude and phase.
In a sense, yeah, it makes calculations much cleaner. And the book introduces complex impedance, too, which combines resistance and reactance, the opposition to changes in current or voltage, into one complex number. AC circuit analysis becomes much more manageable.
Okay, makes sense. Simplifying the AC world. And for three-phase power, which is everywhere, it covers star and delta connections.
Absolutely essential. These are the two main ways you can connect the three sets of windings in a three-phase machine, whether it's a generator stator or a motor stator.
Star, sometimes called Y, and delta.
Exactly. The book clearly shows the wiring diagrams for both, and importantly, gives them mathematical relationships. You know how the voltage and current inside one winding the phase values relate to the voltage and current you measure between the lines connecting to the machine, the line values. Understanding that difference is fundamental.
Crucial for hooking things up correctly and analyzing performance. And then it tackles something called symmetric components. That sounds like a way to deal with things when they aren't perfect.
That's precisely it. In an ideal world, your three-phase voltages and currents are perfectly balanced, same size, perfectly spaced, 120 degrees apart. But reality, not always so neat. You get unbalanced loads, maybe faults.
Things get messy.
Right. Symmetric components are this really clever mathematical technique. It lets you take any unbalanced three-phase system and decompose it, break it down into three separate sets of balance systems.
Three balanced systems.
Yeah. A positive sequence system, the normal rotating one, a negative sequence system, which rotates the opposite way, and a zero sequence system, where all three phases are in sync. Analyzing each of these balanced sets is way easier.
And then you combine the results.
Exactly. Combine the results to understand the original unbalanced behavior. It's like analyzing a complex sound by breaking it into its pure frequency components. A very powerful tool for fault analysis and protection.
Huh. Neat trick, taking a wobbly system and seeing it as three smooth ones. The book also hits on mutual inductivity. That's about coils interacting, right?
Yes. If you have two coils near each other, their magnetic fields interact. The book uses that example to show something fundamental. The mutual inductance from coil 1 to coil 2, L12, is always equal to the mutual inductance from coil 2 to coil 1, L21.
So the influence is symmetric.
It is, and it derives this from a core principle. The total magnetic energy stored doesn't care which order you energize the coils in, it has to be reciprocal.
Makes intuitive sense. The interaction should look the same from either side. Okay, and finally for this foundational chapter, it covers iron losses, the energy wasted in the machine's core.
Yeah, the unavoidable losses that happen in the iron parts when the magnetic field inside them is changing, which it constantly is in AC machines and even DC machines to some extent. Two main culprits here.
Okay.
First, eddy currents. These are like little swirling electrical currents induced within the iron core itself by the changing magnetic flux. They just flow around in the iron and generate heat-wasted energy.
How do you fight those?
The main weapon is lamination. You build the core from thin sheets of iron, insulated from each other. This breaks up the paths for those eddy currents, making them much smaller. These losses go up fast with frequency and flux density, by the way.
So thin sheets are key. What's the other loss mechanism?
Hysteresis loss. This is more about the magnetic material itself. It takes energy to keep realigning the tiny magnetic domains inside the iron as the magnetic field direction flips back and forth, cycle after cycle.
Like magnetic friction almost?
Kind of, yeah. This loss is related to the area inside the material's BH loop, its hysteresis loop. It's also proportional to frequency. Minimizing both eddy currents and hysteresis is a huge part of designing efficient machines.
Got it. Okay, wow, that's a really packed foundational chapter. Now let's move into chapter 2, which focuses on DC machines. These feel a bit old school, but they're still really important, right?
Oh, absolutely. They were the workhorses early on, and they still have many important applications, especially where precise control is needed or in specific power ranges. The book starts with the basic anatomy.
What are the main parts?
You've got the stationary part, the stator, which usually holds the field poles. These create the main magnetic field. Then there's the rotating part, the rotor, also called the armature, which has the windings where voltage is induced and torque is made.
And the unique bit for DC machines.
The commutator. It's that segmented copper cylinder on the rotor shaft. And you have brushes, usually carbon, that press against it. The commutator and brushes act together like a mechanical switch.
A spinning switch. What's its job exactly? Why is it so crucial?
Its main function is ingenious, really. It ensures that the current flowing in the armature conductors under a specific magnetic pole always flows in the same direction, even as the rotor spins.
Ah, so it reverses the connections at just the right moment.
Precisely. As a coil passes from under a north pole to a south pole, the commutator switches its connection to the external circuit via the brushes. This keeps the torque acting continuously in one direction. Without it, the torque would reverse every half rotation.
Clever.
Yeah.
Mechanical rectifier almost. Okay, so how does this setup generate voltage and torque? Back to fundamentals.
Back to Faraday and Lorentz, basically. Voltage generation. As the armature conductors spin and cut through the stator's magnetic field, Faraday's law says a voltage is induced in them. The stronger the field, the more conductors, the faster the spin, the higher the voltage.
Makes sense. And torque.
Torque comes from the interaction between the current flowing in those armature conductors, fed in through the brushes and commutator, and the magnetic field from the stator. It's the Lorentz force, essentially. The right-hand rule tells you the direction. Add up the forces on all the conductors, and you get the turning force, the torque.
Okay, motion plus field equals voltage. Current plus field equals force. Got it. The book then boils this down to three main equations for a DC machine.
Yes, these are fundamental for analysis. You have the equation for the induced voltage, often called back EMF when it's acting as a motor because it opposes the applied voltage. Then the equation for the electromagnetic torque produced. And finally, the terminal voltage equation, which connects the voltage you apply at the terminals to that induced voltage, the armature current, and the armature winding's internal resistance.
And these let you figure out how the machine behaves.
Exactly. You can combine and rearrange them to derive the speed characteristic, how speed changes with load, and define key things like the no-load speed, speed with zero torque, and the stall current, current when the rotor is stopped but voltage is applied.
Okay, framework established. Now the book dives into the different types of DC machines. Let's start with separately excited ones. What's special there?
Separately excited means the field winding on the stator, the one making the main magnetic field, has its own independent DC power source. It's separate from the power supply going to the armature.
So you can control the field strength and the armature voltage independently.
Exactly. That's the big advantage. It gives you lots of flexibility for controlling speed and torque. The book shows how changing armature voltage primarily affects speed, while changing field current affects both speed and torque capabilities. Reversing the armature voltage polarity reverses rotation. Great for precise control applications.
Versatility. Okay, next up, permanent magnet DC machines, PMDC.
Right. Here, instead of a field winding, you just use permanent magnets on the stator to create the field.
What are the pros and cons there?
Pros. Simpler construction, no field winding or power supply needed, so often smaller, lighter, cheaper, and more efficient because you don't have those field winding losses. They can also have better dynamic response.
Sounds good. Downsides.
The main one is you can't easily control the field strength. It's fixed by the magnets. So speed control is usually done by varying the armature voltage, or sometimes by adding resistance in series with the armature, which is lossy. The book discusses the magnetic properties needed for the magnets, shows the analysis using Ampere's law for the magnetic circuit, and gives the speed-torque equations.
Simplicity and efficiency, but less control over the field. Got it. Then shunt-wound DC machines. How are they wired?
Shunt means parallel. So the field winding is connected in parallel, or shunt, across the armature terminals. Both get the same supply voltage.
And how does that affect performance?
These are known for having a relatively stiff speed characteristic. That means their speed doesn't drop much when you increase the mechanical load. They tend to run at a fairly constant speed, which is useful for things like lathes or fans where you want consistent operation. They also have a stable no-load speed.
Stiff speed. Good for consistency. What about the opposite almost? Series-wound DC machines.
Yeah, here the field winding is connected in series with the armature. So the same current, the armature current, flows through both.
How does that change things?
Dramatically. Because the field strength now depends on the armature current, which depends on the load, these machines have a drooping speed characteristic. Speed falls off significantly as load increases. But the flip side is they produce incredibly high starting torque.
Why is that?
Because at start, current is high, which means the field is strong and the armature current is high, giving you a torque proportional to current squared, roughly. Perfect for starting heavy loads like old trams, trains, cranes.
High starting grunts, but a potential downside.
Yes, you have to be careful. If the load is removed or becomes very light, the current drops, the field weakens, and the motor can speed up uncontrollably run away. They should generally always be connected to a load.
Okay, noted. High torque, variable speed, risk of runaway. Then there are compound DC machines. A mix.
Exactly. They have both a shunt field winding in parallel and a series field winding in series, so they blend the characteristics.
Trying to get the best of both worlds.
Pretty much. You can get better starting torque than a pure shunt machine, but better speed regulation and a limited no-load speed compared to a pure series machine, avoiding the runaway problem. They offer a good compromise for applications needing both decent starting torque and reasonably stable speed.
A versatile middle ground. Okay, the chapter also mentions generating variable voltage, and then this thing called armature reaction. What's that about?
Armature reaction is basically an unwanted side effect. The current flowing in the armature windings creates its own magnetic field, and this armature field interacts with, distorts, and tends to weaken the main magnetic field produced by the field poles.
So the motor's own operation messes with its main field.
Yeah. It can cause problems like reducing the net torque, shifting the ideal commutation point, and potentially causing more sparking at the brushes.
Not ideal. How do designers deal with it? The book mentions commutation poles, or interpoles.
Right. Interpoles are small, extra poles placed physically between the main stator poles right in the zone where commutation happens. Their windings are connected in series with the armature.
So they see the armature current.
Exactly. They create a localized magnetic field that directly opposes the field produced by the armature current in that commutation zone. Their job is to cancel out the harmful voltage induced in the coils undergoing commutation, leading to much smoother spark-free operation, especially under heavy loads and high speeds. Improves efficiency and brush life.
A clever fix for an inherent problem. Okay, that covers DC machines pretty thoroughly. Now, the book shifts gears significantly in Chapter 3, introducing rotating field theory. This feels like a really core concept for AC machines.
It absolutely is. This is the foundation for understanding how most AC machines work: induction motors, synchronous motors, generators, pretty much the bulk of industrial and utility machines.
So what's the starting point?
Well, the chapter acknowledges some practical details like slot leakage flux that doesn't cross the air gap usefully, and it makes a common assumption that the iron core is infinitely permeable, meaning magnetic flux prefers the iron path vastly over air.
A simplifying assumption for analysis.
Yes. Then it explains how the current flowing in the stator windings, arranged in slots around the stator's inner surface, creates a magnetomotive force, or MMF. That's the driving force for the magnetic field.
Okay, MMF from the currents.
Yeah.
And the book distinguishes between alternating and rotating MMF.
Crucially, yes. If you just have one coil with AC current, you get an MMF that pulses in strength but stays fixed in space, an alternating MMF. But if you arrange multiple coils spatially, say 3 sets of windings 120 degrees apart physically.
Like in a typical three-phase stator.
Exactly. And you feed them with balanced 3-phase currents, which are themselves shifted in time by 120 degrees. The combined effect is magical. The resultant MMF wave has a nearly constant magnitude, but it rotates smoothly around the air gap.
The field itself spins.
Yes. The book uses Fourier analysis to show this, and also points out that the physical distribution of the windings isn't perfect, so you can get unwanted spatial harmonics in the MMF wave, even with pure sine wave currents.
Ah, so the winding layout matters for the quality of the rotating field. And that brings in the winding factor.
Precisely. The winding factor is a number that tells you how effective a specific winding layout is at producing the main fundamental component of the rotating MMF, the one you want, compared to an ideal concentrated winding. It also reflects how well it suppresses those unwanted harmonics. Factors like how coils are spread out, distribution factor, and if they span less than a full pole pitch factor, contribute to it.
So it's a measure of winding design quality. And this rotating MMF creates the rotating air gap field.
That's the key outcome. Balanced three-phase currents in a properly designed stator winding produce this magnetic field that physically rotates within the air gap between the stator and rotor. Its speed is called the synchronous speed.
And what determines that speed?
Two things. The frequency of the AC power supply, like 50 or 60 hertz, and the number of magnetic pole pairs the stator winding is designed to create. Higher frequency means faster speed, more poles means slower speed for a given frequency.
Got it. Frequency and pole pairs set the synchronous speed. Now, the chapter then sets up the idea of induction machines by talking about induced voltage and slip. How do they fit in?
Okay, so you have this rotating magnetic field from the stator. In an induction machine, the rotor isn't directly connected to the power supply. The stator's rotating field sweeps past, or cuts, the conductors in the rotor winding.
Faraday's law again.
Faraday again. This induces a voltage in the rotor conductors. And since the rotor winding is typically a closed circuit, like in a squirrel cage, this voltage drives currents within the rotor.
But for induction to happen, there has to be relative motion, right?
Exactly. The rotor cannot be spinning at the exact same speed as the stator's field. It has to spin slightly slower. This difference in speed is called slip.
How is slip defined?
It's usually expressed as a percentage or a fraction. It's the synchronous speed minus the actual rotor speed, all divided by the synchronous speed. So 0 slip means rotor is at synchronous speed, no induction, and a slip of 1 means the rotor is stationary. The frequency of the voltages and currents induced in the rotor is directly proportional to the slip times the stator frequency.
So slip is absolutely essential for an induction motor to work. If it reached synchronous speed, it would stop producing torque.
Precisely. No slip, no relative motion between field and rotor conductors, no induced rotor current, no torque. Slip is what makes it go. And the chapter then connects this slip value directly to the amount of torque and power the machine develops.
Fascinating. Okay, so Chapter 3 lays that theoretical ground. Then Chapter 4 zooms in specifically on induction machines. These are the real workhorses of industry, aren't they?
Hugely common, yes. Robust, relatively simple, reliable. So the chapter looks at their construction stator with its three-phase winding rotor, either squirrel cage or wound rotor with slip rings, separated by that crucial small air gap.
And the principle relies on that rotating field we just discussed.
Entirely. Stator field rotates, induces currents in the rotor. Those rotor currents interact with the stator field, Lorentz force again, creating torque that makes the rotor spin, trying to catch up with the field but never quite managing it because it needs slip.
Right. And the book introduces an equivalent circuit. That sounds useful for analysis.
Extremely useful. It's an electrical circuit model that represents the behavior of the induction machine. It includes resistances and reactances for both the stator and the rotor windings, and crucially, components that model the magnetic coupling between them across the air gap. It allows engineers to calculate performance currents, power factor, torque, efficiency, without needing complex field theory for every calculation.
A practical tool. Then there's something called the Hallen diagram or circle diagram. What's that about?
It's a graphical method, a bit old school now, perhaps with computers, but conceptually very powerful. It plots the locus, the path of the stator phase current vector in the complex plane as the slip varies from 0 synchronous speed to 1 standstill.
A picture of current behavior.
Exactly. From this circle and a few construction lines based on machine parameters from the equivalent circuit, you can graphically determine almost all the machine's steady-state performance characteristics. Input power, output power, torque, efficiency, power factor, slip, all as a function of load. You can easily see the stall current at slip 1, 2.
Like a complete performance map on one diagram? Cool. The book must then discuss the torque-slip characteristic curve. That sounds vital.
Oh, it's fundamental. It's a graph plotting the electromagnetic torque the motor produces versus the slip, or sometimes speed. It has a very characteristic shape.
What does it look like?
Starts at 0 torque at 0 slip, synchronous speed. As slip increases, speed decreases, torque rises, reaches a peak value called the pull-out torque or breakdown torque.
The maximum torque the motor can sustain.
Yes. And then, as slip increases further towards 1 standstill, the torque actually decreases. Understanding this curve is critical for matching a motor to a load, ensuring it can start the load, and operate stably in the desired region, usually on the slope before the pull-out torque point.
So you know its limits and its sweet spot. What about controlling the speed of these motors? The chapter covers open-loop methods.
Yeah, open loop meaning you change an input parameter but don't actively measure the speed and adjust based on feedback. For wound rotor motors, the ones with slip rings, you can change external resistance connected to the rotor. More resistance shifts the torque curve, allowing some speed control, but it's inefficient due to losses in the resistors.
Yeah, else?
The main method today, enabled by power electronics, is changing the frequency of the AC supply to the stator. Since synchronous speed depends directly on frequency, changing the frequency changes the motor speed proportionally, more or less. You usually need to adjust the voltage to V-Hertz control to maintain proper flux.
Frequency control. That sounds flexible. Any other ways?
Less common is pole changing. Some motors have special windings that can be reconnected to change the number of effective magnetic pole pairs, which changes the synchronous speed in discrete steps, like half speed or full speed.
Okay, changing resistance, frequency, or poles. The book also mentions star-delta starting. What problem is that solving?
The problem is high starting current. Induction motors can draw like 5 to 8 times their normal running current when started directly across the line voltage. This huge surge can cause voltage dips, trip breakers, stress the system.
Not good.
So, star-delta starting is a common reduced voltage starting method. You initially connect the stator windings in a star-Y configuration. In star, each winding only sees one year about 58% of the line voltage.
Which reduces the current.
Yes, significantly. Starting current is reduced to about 1/3 of the direct online starting current. Starting torque is also reduced to about 1/3. Once the motor speeds up, you switch the connections to delta, applying full voltage for normal running.
A softer start. Makes sense. Then, the doubly fed induction machine, DFOM. How's that different?
Okay, standard induction machine. Stator powered, rotor currents induced. Doubly fed, stator powered from the grade, and the rotor, which must be a wound rotor type with slip rings, is also connected to a power electronic converter.
So power can flow in or out of the rotor, too.
Exactly. That converter injects controlled voltages at slip frequency into the rotor. This gives you much wider speed control, typically 30% around synchronous speed, and also allows control over reactive power. Hugely important for large wind turbines, for instance.
More complex, but more control. Lastly, for induction machines, the squirrel cage rotor, the common one, and skewing the bars. Why twist them?
Right, the squirrel cage is simple and rugged. Bars embedded in the rotor iron, shorted by end rings. Looks like a cage. Skewing means the bars aren't exactly parallel to the shaft. They're slightly angled or twisted across the length of the rotor.
Why do that?
It's mainly to reduce noise and vibration and to smooth out torque production. It helps cancel out some of the undesirable effects caused by magnetic field harmonics, those imperfections in the rotating field due to slots and windings. Skewing averages out these effects along the rotor length, reducing torque ripple and magnetic noise.
A subtle but important design feature for smoother running. Okay, deep breath. Chapter 5, move to synchronous machines. What's the defining difference from induction machines?
The name gives it away. Synchronous. The rotor rotates at exactly the same speed as the stator's rotating magnetic field. Perfect synchronism.
No slip needed here.
None at all for torque production in steady state. It achieves this because the rotor has its own magnetic field source that locks onto the stator's rotating field and gets dragged around with it.
How is that rotor field created?
2 main ways. Either you have a winding on the rotor fed with DC current, through slip rings typically, creating an electromagnet. Or, increasingly common, you use permanent magnets embedded in or mounted on the rotor. The book describes both constructions, the stator winding, similar to induction machines, and introduces the equivalent circuit, which crucially includes the internal generated voltage, the excitation voltage, set by that rotor field.
Locked in step. The book distinguishes between cylindrical rotors for high speed and salient poles for low speed.
Yes, the rotor design depends heavily on the speed and the prime mover. High-speed generators, like those driven by steam turbines and power plants, turbogenerators, use smooth, solid, cylindrical rotors. They need the mechanical strength for high speeds and provide a more uniform air gap.
And salient pole.
Those are for lower speeds, typically driven by hydroturbines or diesel engines. They have distinct protruding poles, salient means protruding, with windings wrapped around them. This construction is better suited mechanically for lower speeds and larger diameters, and the non-uniform air gap actually offers some advantages in certain cases.
Design follows function and speed. Okay, a key concept seems to be the power angle or load angle. What is that?
The power angle, delta, is the electrical angle difference between the magnetic axis of the rotor's field and the axis of the stator's rotating magnetic field. It's absolutely fundamental.
Why? What does it tell you?
It directly determines how much real power the machine is transferring. For a generator, as you put more mechanical torque in, the rotor pulls slightly ahead, delta increases, and more electrical power flows out. For a motor, as you apply more mechanical load, the rotor falls slightly behind, delta becomes negative by convention, and more electrical power flows in.
So it's a measure of load.
Yes. And crucially, there's a limit. The power transferred is proportional to the sine of the power angle. There's a maximum power and torque that occurs typically around delta equals 90 degrees electrical. If you try to push beyond that, the machine loses synchronism, slips a pole, and can stall. That limit is the pull-out torque.
So the angle indicates power flow and stability margin. What about synchronizing torque?
That's the inherent torque that pulls a synchronous machine back into step if it gets slightly disturbed. If multiple generators are running in parallel on a grid and one momentarily speeds up or slows down, its power angle changes, creating a restoring torque that pushes it back towards the correct synchronous position relative to the others. It's what keeps the grid stable.
An automatic stabilizing effect. Good. The chapter also mentions generator versus motor modes.
Yeah, it's just about the direction of power flow, determined by that power angle. Positive delta, rotor leading slightly, means generator mode, sending power out. Negative delta, rotor lagging slightly, means motor mode, taking power in.
Simple enough. And finally, load characteristics in isolated operation.
This looks at what happens to the generator's terminal voltage if it's running by itself, not connected to a huge grid, and you start connecting loads. As you draw more current, the voltage at the terminals tends to drop due to internal voltage drops across the machine's synchronous reactance and armature resistance. How much it drops depends on the machine design and the power factor of the load. Understanding this voltage regulation is important.
Okay, clear. So we've covered DC, induction, and synchronous machines. Chapter 6 then zooms in on permanent magnet-excited rotating field machines. We saw PMs in DC. How do they work in AC rotating field types?
It's basically applying the permanent magnet idea to synchronous machines. Instead of a DC-fed field winding on the rotor, you use strong permanent magnets.
What are the advantages here?
Big ones. You eliminate the field winding, the DC excitation source, and crucially, the slip rings and brushes needed to get DC onto the rotor. That means higher efficiency, no field winding losses, potentially higher power density, more compact, better reliability, no brushes to wear out, and simpler construction in some ways.
Sounds very attractive. How are the magnets arranged?
The book mentions two main styles. Surface-mounted, SPM, where magnets are glued or fixed to the outside of the rotor core, and interior permanent magnet, IPM, where the magnets are buried inside the rotor laminations. IPM designs can offer some extra reluctance torque and better flux weakening capabilities. The equivalent circuit is similar to a synchronous machine, but the excitation voltage comes from the magnets and isn't easily controllable, though its effects can be managed.
Right, the field is fixed by the magnets. Now, the chapter explains brushless DC motors, BLDCs. You mentioned the name is a bit tricky.
Yeah, it is a bit confusing, because internally, a BLDC motor is essentially a permanent magnet synchronous motor. It has a PM rotor and a wound stator. The brushless DC name comes from its behavior and how it's controlled. It uses electronic commutation instead of mechanical brushes. Sensors, like Hall effect sensors, detect the rotor's position, and a controller rapidly switches the currents in the stator windings in a specific sequence, often trapezoidal waveforms, to create a rotating field that stays roughly 90 degrees ahead of the rotor magnet's field. This produces torque similar to a brushed DC motor torque, roughly proportional to current, speed roughly proportional to voltage.
So the electronics mimic the function of the commutator and brushes, making it behave like a controllable DC motor, even though it's technically an AC synchronous machine inside.
Exactly. That's the key. It combines the robustness of AC machines with the controllability often associated with DC motors.
Clever. The book notes detailed analysis for IPMs comes later using space vector theory. Okay. Before that, Chapter 7 briefly introduces reluctance machines. These sound different again, torque without magnets or field windings.
That's the fascinating part. They work on the principle of minimum reluctance. A magnetic circuit always prefers the path of lowest magnetic resistance, or reluctance. Reluctance machines exploit this. Synchronous reluctance motors have a rotor carefully shaped, with internal flux barriers often, so that the reluctance seen by the stator's rotating field changes significantly depending on the rotor's angle. The rotor naturally tries to align itself to the position of minimum reluctance relative to the field, and this tendency creates torque, pulling it along synchronously.
So it's pulled along by wanting to complete the magnetic circuit easily.
Essentially, yes. Then there are switched reluctance motors, SRMs. These have salient poles on both the stator and the rotor. You energize stator windings sequentially, one phase at a time. The energized stator poles attract the nearest rotor poles towards alignment, causing rotation step by step. Torque comes from this tendency for alignment. No magnets, no rotor windings needed. Simple and robust, but control can be complex to get smooth torque.
Using magnetic alignment forces. Interesting. Chapter 8 then touches on small, single-phase machines. Ubiquitous in homes, but single-phase AC doesn't naturally create a rotating field.
Correct. Single-phase AC just creates a pulsating field, grows and shrinks, but doesn't rotate. So single-phase motors need a trick to get started.
Like what?
The book mentions universal motors first. These are actually series-wound DC motors designed to run on AC2. They work because the field and armature currents reverse together. Very common in power tools, vacuum cleaners.
Ah, okay. What about induction motors on single-phase?
For single-phase induction motors, you need an auxiliary starting mechanism. Split-phase motors use a separate starting winding with different resistance reactants to create a phase shift. Capacitor start motors add a capacitor in series with the starting winding for a bigger phase shift and more starting torque. Shaded pole motors use a simple copper ring around part of each pole face to delay the flux there, creating a very weak rotating effect to get it going. They're cheap, but inefficient.
Ingenious tricks to get things spinning from one phase. Okay, let's jump to Chapter 11, Space Vector Theory. This sounds like a powerful modern tool. What is it?
It really is. It's a mathematical transformation that lets us represent the three time-varying phase quantities, like currents, i.e., of a three-phase system as a single rotating vector in a complex plane.
One vector instead of three waveforms.
Exactly. This space vector has a magnitude related to the overall amplitude of the three-phase system and an angle representing the instantaneous spatial orientation of the combined magnetic field or current distribution. The book explains the math to go from the three phases, ABC, to this complex space vector, often represented in a stationary DQ frame.
Why is that so helpful?
It massively simplifies the mathematical models of AC machines. Instead of three coupled differential equations for the phases, you often end up with just one vector differential equation. This makes analysis, especially of dynamic behavior and control system design, much more tractable and insightful.
Streamlines the math. Got it. And it can be seen as a transformation to a rotating two-phase system.
Yes, that's a common interpretation. The space vector can be thought of as representing the state in an equivalent two-phase system, often called alpha-beta or DQ axes. If you then make this DQ coordinate system rotate, often synchronously with the rotor flux or the stator field, the equations can become even simpler, sometimes turning AC quantities into DC-like quantities in steady state. This is the foundation of field-oriented control.
Linking it to control. And port calculation.
Yes, space vectors provide elegant ways to express instantaneous electromagnetic torque. It often involves a vector cross product, like the cross product of the stator flux linkage space vector and the stator current space vector. Very compact and physically meaningful.
Powerful math indeed. Okay, so armed with space vectors, chapters 12, 13, and 14 dive into dynamic operation and control of AC machines. Chapter 12 focuses on induction machines.
Right. This chapter uses space vector theory to analyze how induction motors behave during transient starting, load changes, etc. And crucially, it introduces field-oriented control, FOC, or vector control.
What's the core idea, FOC?
It's about decoupling control. Yes. It looks at things like stability power oscillations between interconnected generators. It explains the role of damper windings, mortiseur windings, which are like squirrel cages embedded in the rotor poles, specifically to damp out these oscillations and improve transient stability.
Like shock absorbers for the electrical system.
Good analogy. The chapter uses space vectors to analyze steady-state operation of both cylindrical rotor and salient pole machines, highlighting the differences caused by saliency, varying inductance with angle. A big topic is the sudden short circuit, analyzing the huge transient currents and torques that occur, which is vital for protection system design. Salient pole transient behavior gets extra attention due to its complexity.
Understanding the rough stuff to keep the lights on. And Chapter 14 applies this dynamic view to the permanent magnet machines.
Correct. It uses space vector models to analyze the steady state and dynamic performance of permanent magnet synchronous machines, PMSMs. A key focus is on control strategies for maximizing torque, especially considering voltage and current limits. This leads to concepts like torque per ampere control at lower speeds and field weakening control at higher speeds.
Field weakening. How does that work with permanent magnets you can't weaken?
Ah, good question. You can't weaken the magnets themselves, but you can inject a component of stator current that opposes the magnet's flux, a negative d-axis current in the rotating frame. This reduces the total air gap flux and, importantly, the back EMF voltage induced by the magnet spinning. Lower back EMF allows the motor to run faster before hitting the voltage limit of the drive, extending the speed range.
Clever. Using stator current to counteract the permanent field. Finally, Chapter 15 and parts of 7 circle back to some other topologies and special topics.
Yeah, it rounds things out, revisits reluctance machines, maybe adding more on controller-specific types, might elaborate further on single-phase motor designs, and it introduces improved concentrated windings.
Concentrated windings, what's the benefit there?
Traditional windings are often distributed over several slots per pole per phase. Concentrated windings wrap coils around single stator teeth. This can lead to shorter end windings, less copper, lower losses, potentially higher power density, and maybe easier manufacturing. The challenge is often managing harmonic content, so the book likely touches on advanced designs that minimize those issues.
Always pushing for better performance and efficiency. Okay, wow. We've really covered a huge amount of ground here, tracing the path through this book.
We certainly have. From the absolute basics of Maxwell's equations, through the workings of DC machines, the crucial idea of rotating fields for AC machines, the details of induction and synchronous types, the rise of permanent magnets, the alternative of reluctance machines, single-phase challenges, and finally the power of space vector theory for modern analysis and control.
It feels like this deep dive, using electrical machines, mathematical fundamentals of machine topologies, PDF as our guide, really does give you that solid first layer of understanding if you're new to the mathematical side and the different machine types.
I think so. It lays out the core concepts, the key equations, the different constructions, and how they all fit together. It's the essential map of the territory.
And like you said, while we hit the highlights, the book itself obviously goes much deeper into the derivations, the calculations, the design nuances.
Absolutely. Hopefully this overview gives you the framework and maybe the confidence to dive into those deeper details in the areas that grab your interest.
Definitely. So, as a final thought for you, the listener, having journeyed through all this, from basic forces to complex control, what single concept or machine design stands out to you as particularly ingenious or elegant in how we harness electromagnetism? It's a field just packed with clever ideas.
It really is. Something to ponder.
Thanks for taking this deep dive with us.